Hi, everybody. My name is Or. By training, I'm a carbonate sedimentologist. As Ude already presented, over the years, my work expanded also to incorporate how that interfaces with paleoceanography and geochemistry. And this talk will get into some of the way these things interact. My talk today will be focused on the Mediterranean, not the one we know now and like to go on holidays at, but how it came to be and how did that affect the production and nature of carbonates rock that we're producing there. About 20 million years ago, we got for the first time something that was similar to the modern Mediterranean. Before that, it wasn't really the Mediterranean, it was the Mediterranean Tethys. And when we think of the Tethyan Ocean, we usually come to mind was the Great Ocean of the Mesozoic. But in the Cenozoic, that ocean was fundamentally transformed until eventually the movement of Africa just wiped it all out, and what was left was the Mediterranean. So, what am I going to talk about today? Today, I'm going to talk about the type and nature of carbonate production in the Mediterranean Tethys before the closure, and how we know what we know about the closure of that basin and the coupling of the Indian Ocean and Mediterranean, and eventually, and then go into what will probably be the meat of the stock, which is the post-closure carbonate production in the Miocene Mediterranean. It's actually rather easy to look at the pre-closure setting, especially in the Middle East, because a lot of what used to be marine environment is now uplifted in all the sutures and the plates we have there. This map here shows 144 sites. My collaborator Giovanni Coletti from University of Milan Bicocca and his students painstakingly digitized for our analysis. And these span sites from the Palaeocene all the way to the Miocene and give us a good idea of how things looked before the closure. For the most part, in the Paleogene, in the Tethyan realm, the dominant carbonate production was by phototrophs, and a small portion of it by heterotrophs, with a little bit and to almost no contribution from non-skeletal material. That was true for the Paleocene as well as Eocene. But this classification is a bit misleading because when we actually looked in details what makes up the bulk of the rock, what was most of the production, it isn't things like corals, which we associate with phototrophs right now. It was actually mostly large benthic foraminifera, which are in this case probably mixotrophs. And this is by a wide margin. And the second most common thing that we found there were red coralline algae. So while this was temperate, this wasn't exactly your necessarily typical tropical factory. It was something a bit different. That's our baseline. This is where we start. But things happened in the Miocene. Before, of course, I can talk about that, I want to talk a little bit about oceanic gateways. Oceanic gateways are relatively small regions where water are exchanged between oceanic basins. Think Straits of Gibraltar, think Bab el-Mandeb or Strait of Hormuz. So these are very small areas that connect two marine bodies. And they're really, really important in oceanography, and especially paleoceanography, because the open and closure of such gateways is fundamental to the regulation of heat and salt and general material transport between the ocean basins. And the Cenozoic was a very exciting time with this respect, because this was a period where energy transfer shifted from meridional to latitudinal, and a lot of that had to do with opening and closing of marine gateways, specifically opening of high latitude marine gateways, such as the Tasman Passage and the Drake Passage, and the closure of low latitude oceanic gateways, which probably the most critical of them was the closure of the Tethyan Seaway. When we get to by the time we get to the Oligocene, there isn't that much left of this great ocean of the Mesozoic. We have the Mediterranean on the west, the Indian Ocean on the east, and in between a very narrow seaway, which we call the Mesopotamian Gateway or the Mesopotamian Seaway, that was connecting these two basins. We know that sometime during the Miocene, that connection terminated. We have a lot of different evidence relating to what was going on, how it was going on, but this was a messy divorce. There were a bunch of factors in play, and figuring out how the sequence of event was going on and the timing is really crucial to put this into the wider oceanographic context, both the global ocean, which is a different talk, and more specifically, how it affects circulation and patterns in the Mediterranean. This wasn't, one thing that was going on. There was, of course, the compression as Africa and Arabia was moving towards Eurasia, but there were interplate volcanism as well, and combination of flexural and thermal doming. All of these worked at the same time to restrict this very narrow seaway. Now, a lot of these the critical areas to go and look at this are not very easy to work at, but we have other tools, such as geochemical tools, that allow us to fingerprint what the ocean was going and which water mass was contributing to where. We don't have a time machine, so we can't go and sample the water, but we can measure things like neodymium isotopes. We can look at neodymium in minerals that form in place, what we call the orthogenic signal, and that tells us something about the water mass in place. Although we have to be careful, the local input can contribute to the local water, and that kind of makes things complicated. To try to mitigate this, what I did was I went and looked at carbonate platforms, because carbonate platforms are decoupled from the continents. They're usually areas where we have a lot more local production than we have input of terrestrial material, so we don't have to deal with those contaminations. And additionally, they're also shallow. And that's kind of important if we want to trace surface water. Looking at the deep water is a bit more complicated. There are other factors involved, but shallow waters, that's a bit easier. So we took samples from the site U14468 in the Maldives, which was one of the sites we drilled when I was there with IODP, and also from Malta, to give us our end member, our Mediterranean and our Indian Ocean end member. And this is a compilation of all that data. The curves that are in blue are the ones we generated. The other ones were generated by other people. And all of these gray bars are markers for that gives us the indication that something happens, that there is restriction, there is movement, there is some interactions. So we took all of that information together, these records, and together with some modeling, it was possible to piece together the story. So originally, the way we looked at that is that until about 20 million years ago, this was an open connection. And then at 20 million, in Malta, we see this big, very rapid drop in the neodymium isotopes, which based on the modeling work suggests that this indicates restriction of about 90% of the connectivity between the Indian Ocean and the Mediterranean. So that phase was probably tectonic, because if we look at our syllable record for the time, nothing really happens at that period. But that brings us to a period where this connection is restricted, maybe intermittent. And then around 13, 14 million years, we have another drop in the neodymium record in Malta. In the Indian Ocean, we see something going on at the same time. And we have a rapid sea level drop that's part of global processes related to the glaciation of Antarctica mostly. And that was probably the end. After that, there was no more connectivity. The gateway was completely closed. Of course, that was based on our knowledge around 2019. 2020, Torpstein and Steinberg, using access to deep wells in the basins from industry, were able to piece together the story of the deep water. And what they were seeing is that between 21 and 24 million years ago, deep water connectivity was already going away. So this is where we are right now with the time. We decided at some point to call these MRS events, Mesopotamian restriction stages, and we have 3 of them. We have MRS 0, which occurred between 21 and 24, which was when deep water circulation was decoupled. Then MRS 1, 20 to 19 million years ago. That is where we're losing most of the surface connectivity and probably all of the intermediate water connectivity. And MRS 2, around 13 to 14 million years, where the connectivity completely and finally terminates. So that's our timeline. We know when things happen. We know what is going on, more or less. Now, with that in mind, we can go back and look at the record in the Mediterranean and put them into context. Now, it's important to contextualize this. And modeling, again, is very helpful in this. The ocean, the Mediterranean before and after is a very, very different place. So if we have a deep gateway, surface flow in the Mediterranean is coming mostly from the Indian, from waters that are more tropical in source. And we have mostly a westbound flow at the surface and then quite vigorous circulation in the deep water. Once we close that connection, surface circulation now, instead of being westbound, is eastbound, then comes back and forms an intermediate water mass that heads out west. And deep water circulation halts almost to a stop. And we're talking about a decrease in velocities of about an order of magnitude in deep water. That's quite significant. So that's the modeling side. What do we actually see? Well, go back to the compilation I started with. If the Palaeocene and Eocene, we're seeing mostly phototrophs with a little bit of heterotroph. But the Oligocene, when things start to narrow down, we start seeing a lot more non-skeletal grains. And as we shift to the Miocene, which is mostly the early Miocene, we lose a lot of these heterotrophs, phototrophs, and we're getting a lot more heterotrophs and also a lot more skeletal grain, because not only is the temperature shifting, because now we're getting cooler water from the Atlantic rather than tropical water from the Indian, also the chemistry changes because the basin is more restricted and is behaving very differently. This is quite amorphous. Let's focus on some more concrete things. This is a 3D model of Palaeocene in Malta from the lower coralline limestone, late Oligocene. Still says Bialik et al., but now my postdoc Falakande is taking over this project. And in this outcrops, we're seeing a large carbonate platform, very well-developed, prograding, healthy system. Well, at least until like 24, 25 million years, then something happened all of a sudden. This is the top of the lower coralline limestone, the same unit in a different outcrop. And at the bottom, next to the water, you can see this very textured part. That's the top of the lower coralline limestone, or this near the top of the lower coralline limestone. That's the part where we are getting things that see a lot of wave energy, bioplastic peck stones and grain stones. Of course, there are some corals, but we're seeing a lot more red coralline limestone and larvae foraminifera, which, as we said, are actually the main constituents of these carbonate factories. But then very, very rapidly, we lose a lot of wave energy, and we switch from what was a wave-active, probably euphotic factory to a mesophotic environment where we're getting these echinoid facies, it's what's called the scutella bed in Malta. And rapidly progress into a deep water facies, and eventually at 24 million years, where deep waters, when we know deep water circulation was starting to shift with the MRS0, we're getting phosphatic hard grounds. So this restriction seems to already kick in and has quite a tremendous effect early on. And it's not unique to Malta. This is the Terra member in Cyprus, slightly younger, but similarly well-developed carbonate platforms with corals and large benthic foraminifera and coralline algae. And in Cyprus, there is some tectonic that convolves into this, but it still reacts in a very similar way. Now, that tectonics is actually kind of beneficial to us. So we've looked at the shallow water reefs themselves, work by that was led by Giovanni Coletti, and also we went to look at the slope, which is quite useful to do because in the slope we have continuous sedimentation even after the carbonates production in the shallow water factory terminates. So we can tease out this story and put it into context. It wasn't very simple to find a good section for this. We eventually managed to compile one not far from a town called Southern Cyprus. And there is a lot going on there. This was a very complicated section to construct because of the tectonics, which we had to tilt back and figure out how to combine things. But once we did all of that, we started seeing that there are really clear variation and changes between this different period, between these early Miocene reef production and what comes afterwards. So in the earliest Vertigillion, around 20 million years ago, we are in slope, in a periplatform slope, in front of a very strong production center, and we get these mass transport deposits that come in and bring forth these massive chunks of corals, as well as large benthic foraminifera. There is a nearby quite significant shallow water factory. But by the late Vertigillion, around 60 million years ago, that's all gone. What we're seeing is only purely a pelagic production. And at the same time, back in Malta, this transition also comes across with a significant facies change from a phosphogenesis environment, that big art ground I showed, to a pelagic environment with silicification, and sedimentation rate shoots up again by an order of magnitude. As we progress into the Langian in Cyprus, around 13 to 14 million years, where we think complete decoupling has happened, there is another shift in sedimentation mode. So we are going from these more pelagic, current active environment into something that's a lot more laminated. You can see that we're not seeing the same patterns. And we started seeing all of these stains in the fin sections, which turns out to be phosphate, and quite a bit of it. And at the same time, in northern Cyprus, work done by the group from Edinburgh showed that we have the initiation of sepals. These aren't what we have in the Paleopleistocene. These are in a much lower frequency, but they behave the same way and have the same character. This thing where the early Miocene reefs suddenly stop, as I alluded to, is not unique to Malta, and it's not unique to Cyprus. This is a regional phenomenon, and that's already been identified by Buchbinder and Esteban in the 90s. There is a reef gap. We are losing the early Miocene reefs, and after that, there is a gap, and then a new phase of reefs. But these are very different reefs. And these late Miocene reefs are smaller. They have a different character. There's a lot more corals in them. But, well, it's hard to see this in the outlook. But if we go offshore Cyprus, a little bit to the south of the Eratosthenes Seamount, this has been drilled by ODP, expedition 160. And we know that there is continuous production there, even into the Middle Miocene, although something happens there and there's a big disturbance even at the core. Looking at seismic that VGR has acquired there, we can tease out the different units, map them out, and characterize the facies, or the seismic facing. And we can characterize these platforms in the early Miocene, in the late Miocene, but in the middle Miocene, something happens. We're getting a completely different character. And that character doesn't really have a reefal center. It's more loose grain material, more what we expect sort of a classic C-type factory, rather than nice big reefs. And that's kind of the shift from these larger platforms in the early Miocene to these grain-dominated facies in the middle Miocene to much smaller platform in the late Miocene. And if we look at producers, here we compiled all the available data on reefs in the Mediterranean, and there's a big change in character. So early Miocene, we see a lot of corals and limited coral and algae being depicted. But going into middle Miocene, so all of a sudden algae and bryozoans and bivalves are becoming very prominent. And then once you get to the late Miocene, corals take over and even more dominantly than they did before. When we looked at the reefs in Cyprus, there was a very clear shift in the way they were, with the character, with what we were seeing there. The early Miocene platforms were a lot bigger, they were a lot wider. There's a lot more large big foraminifera there, corals, coral and algae, but they were also deeper. They were based on the coral and algae that was there, they were mesophotically dominated. But in the late Miocene, they have very, very different character. They're a lot narrower, they're a lot smaller, and they're mostly shallow water, they're mostly euphotic. This is not where we started from. And we need to remember that the Mediterranean had two gateways in the Miocene. It had the gateway in the eastern side, connecting it to the Indian Ocean, and it had one more gate, and it had another gateway in the east, in the west, connecting it to the Atlantic. But the same processes that were closing it on one side were also affecting it on the other side, and a little bit in between. Looking at sea level data, looking at facies in the middle of it in Malta, it was clear that during the Tritonian and Messinian, the middle, this Tunisian Sicilian high was going up. We're seeing a shallowing upward phase. We're seeing two shallowing upward cycles, and there are some geochemical indication that there is a decoupling between the eastern and the western basin. And part of that decoupling has to do with ongoing uplift. Work that was done by me and my collaborator, Israelite, from the University of Granada. We looked at the evolution of canyons in the Eastern Mediterranean. And there is definitely uplifts and interactions with the structure there, because it's not only that there is incision and possibly even submarine incision. That incision gets filled first with pelagic material and eventually in the late Miocene shallow water carbonates. So there are phases of uplift, but also secessions where carbonates can establish themselves. But if we have this uplift going in the middle as well, it has a side effect. And that side effect is that circulation is becoming restricted. And work that was done in Crete is reconstructing sea surface salinity, shows that by the late Miocene, even before the salinity crisis, sea surface salinity was going up. Modern sea surface salinity in the Eastern Mediterranean is around 39 plus PSU. They are reconstructing values that are in excess of 43, which is Red Sea values. Very, very salty waters, quite warm. This basinal decoupling had an effect on carbonate production. You get to the late most Miocene, and we go to southern Spain, see these gorgeous carbonate platforms in the Solvos Basin. Very large platforms, very well developed. We go in the orders of tens of meters in thickness. We go and look at the equivalent unit in Malta, it's a lot smaller. By the time we get to Cyprus or the Israeli margin, they are tiny in comparison. So this salinity and probably nutrient gradient that was forming with this increased basinal restriction was affecting the way carbon was being produced at different places. And then there was salt, and everything died. So, to wrap this up, surface water exchange across the last vestiges of the Tethyan Ocean connecting the Eastern Mediterranean to the Western Indian Ocean terminated in two phases in the early Miocene. First phase was around 20 million years ago, which was most of it, and then whatever was left was terminated around 14 million years ago. This loss of this water source from the Indian Ocean and the shift in reorganization circulation, it shifted everything. It shifted temperature, it shifted salinity, it shifted nutrient state. It essentially reshaped the Mediterranean and also its outflow, which topic for another day maybe. It changed the North African and European climate, and it radically altered the marine habitat and the communities in the region and the carbonate factors we got out of these. This was a crisis. It led to a reef gap, and what we got after that was not what we had before. This work has been going on for quite a while, with a lot of collaborators and sponsors that I have to thank. Of course, my various collaborators on this. Without this, I don't think I could have done half this work. And there is an entire separate story in the Indian Ocean side. But that's a tale for another day. My email is here. Feel free to contact me if you have any follow-up to that. And I think now I need to open the stage for questions.